some personal thoughts about density functional theory and correlated materials and so on. The second part, this has been already covered by Ari, and then I will just quickly show you, how to calculate EPR. But the input files is so similar and so simple, and very similar to the one of NMR that I will probably do this very quickly. So part one. So this is an EPR device. So it is much smaller than the one used in NMR. I think it's basically the size of this podium, and you don't need to very strong magnetic fields in this case, so you can simply use some electromagnets. In the case of NMR, instead, you have to go to sort of from 10 to 20 Tesla, so you need a cryomagnet, so you need liquid helium to cool down your magnets. So this is a very convenient device, and basically the sample goes here in the middle between the expansions of the two magnets, and the principle is the same. And this is a typical EPR spectrum. So EPR stands for electron parametric resonance. So now we are not probing the resonance of a nuclear spin, but we are probing the resonance of an electron spin. And can be used to study paramagnetic defects in solids, radicals, proteins for instance, radicals in proteins or in organic molecules. By parametric defects, I mean that when you have a defect in a solid which has one unpaired spin. So this unpaired spin, can be flipped up and down, and the EPR basically measures this. I remind you that also radicals are molecules with unpaired spins. Those are basically the same. And it is important because the resonance of the spin is very sensitive to the local geometry. And for instance, it can give you the local symmetry of your defects. Imagine you put some gold atom in silicon. So by measuring the components of the G tensor, this can tell you, is this gold atom sitting in a octahedral position? Is it sitting a little bit offside or not? So it can give you the symmetry. And it is also sensitive to the electronic structure. I will show you later that you can basically measure your wave function using EPR. And the G tensor is basically probing, for instance, the crystal field. So you can not only get the local geometry, but also the local spin state, because your impurity can be 1/2 or 3/2, can have more than one pair of spins, and so on. And basically, you can also measure the famous crystal field that you find in solids and in organic complexes. And moreover, it's a non-destructive technique, so you can reuse your sample after that. And you need very small sample, very small amount of matter, so you don't have to synthesize a lot of material, because it is very sensitive, and you can also probe very dilute spins. So basically, you can have a very low concentration of defects. You can still get a good spectrum. So here is an example of an EPR spectrum. Generally, what the experimentalists they plot the derivative. So this is a magnetic field. This is basically the derivative of the absorption, like we do in NMR. They plot the derivative because by plotting the derivative, you put in evidence a lot of the feature. Otherwise, if you plot just the absorption spectrum, you will see just a broad feature with the shoulders and so on. By taking the derivatives, when you get peaks and so on, you put in evidence, the structure of the spectrum. So just to repeat, so this is the principle of magnetic resonance spectroscopy. Now we put our electron spin inside an external magnetic field, and we look for the effective magnetic field acting on the spin, so that it is the induced. And this is the same, this is then split by the magnetic field. Then you send an electromagnetic wave, and whenever an electromagnetic wave matches this transition frequency, you get a dip in the absorption spectrum. So for EPR, I think they use microwaves. And why this is wrong? Because when you apply a magnetic field to a material, right? So you will induce by the Lenz's law some orbital current. So the electron will start orbiting, but the electron orbiting will create an extra. So the famous induced magnetic field. And in general, for instance, because of the Lenz's law, this is opposite to the one that you apply. So the amount of screening, so this is basically the origin of what we were asking before. This is basically the origin of the screening in the chemical shift and also in the EPR, is how much they induce currents that create an opposite magnetic field on your system. So it's a sort of screening, not a shielding. But the name shielding is very popular in the chemist community. So, if you remember, in order to interpret the NMR spectra, there were some tables, basically for hydrogen and carbon. The resonances of several chemical groups are all tabulated. So Ari showed you a table with the chemical shift of the hydrogen. They all cluster in different positions so that you can interpret easily your results. But basically you can do it only for hydrogen and carbon, 13. In the case of EPR spectrum, the interpretation is more involved. And that's why in this case we need to go back to calculation in order to help the experimentalist. So as I said before, I mean, the basic quantity we have to look at is the total magnetic field acting in your system, which is the sum of the external magnetic field that you apply, plus the induced one. This field is the one induced by the orbital currents. And who is responsible for this induced magnetic field is the spin-orbit interaction. So basically, you have a nucleus. So the blue line here I meant to represent the orbital angular momentum of an electron. When you turn on a magnetic field, so the electron the orbital part starts spinning around, and this spinning L angular momentum electron can couple to the spin of your electron. This is called spin-orbit interaction. There is also, because it's called spin other orbit interaction. This is when the angular momentum comes from another atom, for instance, and this is much smaller. But then the magnetic field acting in your system contains also a term, because some nuclei they have magnetic moments, and so they generate a small magnetic field. And this magnetic field can interact with the electron spin, and this is called hyperfan interaction. And then, if you have, for instance, more than one ampere spin, you have to take into account the magnetic field generated by each one of these electronic spins. This is called zero field splitting. This is just nomenclature. Zero field splitting because this one, of course, does not depend on the strength of the external magnetic field. Right? This is there also if you turn on the external magnetic field. So, as I said, so the experimentalist, the way it works is that they break down an effective spin Hamiltonian. So if you couple all these terms together, so basically you get three terms. Mostly you get three terms. These are the most important terms. So this one, if you look at it, is nothing other than the Zeeman term, right? When you couple a spin to a magnetic field, is S dot B. The only difference is that here you put a tensor in between, because this can depend on the direction of the. If you have a crystal, depends on the direction in which you apply your magnetic field, and to the crystallographic direction, because the energy of the spin will depend also on the crystallographic direction because of spin orbit. Now, so this couples the external magnetic field to the electron spin. The hyperfine term instead couples so the nuclear spin with your electron spin, and these are called hyperfine couplings. Also, those are tensors, generally in solids. And finally, the zero field splitting is just coupling two different spins together. So the way it works is that the experimentalists, they need to know a little bit what is the electronic structure, I mean, what is the configuration of the molecule of the system that they are studying. And generally, they draw this kind of diagrams. This is an example for a spin 1 alpha, which is coupled, for instance, to a nucleus which has spin 1, right? So if you discard for a moment the hyperfine coupling, if you have a spin 1 alpha, you get in a magnetic field you get this Zeeman splitting, right, which is represented by these two. So plus 1 half minus 1 half. Then imagine you have a positive hyperfine coupling, and you have close by a nucleus with spin 1. So spin 1 can have plus 1, 0, minus 1, right? The Z component of the spin. And so this is further split by the hyperfine coupling. So this is positive, so it means that when this is negative, you lower the energy by putting the plus 1 here. If you go for spin 1 alpha, right, in order to lower the energy, you have to have the minus 1 here. So this is the IZ, actually it is the MI, so the Z component of the nuclear spin. And the selection rules for the optical absorption are those one. So since the photon carries one quantum of angular momentum, so delta ms must be equal to plus minus 1. But delta mi, so because the electromagnetic field doesn't couple to the nuclear spin, it's 0. So now if you draw all the possible allow the transition, you get this one, because it goes from the mi plus 1 plus 1, this one, and this one. You get basically these three lines. And then, so these are three frequencies of absorption. And then this will give you basically an absorption spectrum with three peaks. The derivative of three peaks is basically this curve here, right? Imagine you have three Gaussians, then you make the derivative, you get this funny shape curve. So basically, the distance between let's say the peaks here is the hyperfine coupling, and the absolute position of the middle line gives you basically the G tensor, because it basically gives you this transition, this energy, right? Okay, and so those are the selection rules for local absorption. And experimentally, what they do is that they hope to know the chemistry of their compound. They draw this diagram. Maybe it's much more complicated because you have more spins or higher spins. And then they simply take the experimental spectrum, they fit it using this Hamiltonian, and they extract this, and the zero field spectrum. So it's just a matter of fitting your spectrum. So now, I mean, coming to the electronic structure, I mean, this is an effective Hamiltonian. I mean, this contains just some parameters. This is just a model, like when you do the easy model or the Heisenberg model. So you just introduce some parameters. But this is not ab initio, right? This is just you write down this Hamiltonian just for your convenience in order to interpret the results in a proper way. But now we have to go back to quantum mechanics because we have to calculate now these parameters instead to extract them from experiments. And yes, and we need what a physical Hamiltonian, something that depends really on coordinates, spin, momentum, and so on. And the one that is used in this problem is the Pauli Hamiltonian. So the Pauli Hamiltonian, I mean, it's kinetic, potential energy, as usual. These are relativistic correction, basically, because when you get close to the nuclear, you have to include this one. But you don't have to take care of that, because this is taken care in the pseudopotential generator. This is called the scalar relativistic approximation. But then, you know that actually the spin does not come out from Schrödinger equation. It comes out only if you go to Pauli or to Dirac equation. And then the next term, the interaction with the magnetic field, is this one. This is the Zeeman term, where G is the G factor of the electron, which is, I mean, it's not 2, it's close to 2 because you have to do, quantum electrodynamics to derive all these digits. And then there is also a relativistic correction. So every time you see a p squared, right, it's a kinetic energy. So it comes from the expansion of the kinetic energy when you add the mc squared term. This is similar to the Zeeman term. In fact, it's called the Zeeman kinetic energy term. And then you get the spin orbit term, which is S dot. This is the nabla. I mean, this is basically the minus the electric field in your system cross the p, the angular momentum. And if you don't recognize this term, if you go in spherical coordinates, you take the nabla in spherical coordinates. This is S dot L. You can convince yourself by doing little algebra that in spherical coordinates this is the S dot L. And then there is the spin at the orbit term, and then I put some dots here because. The most important quantity here, to get a sense of the order of magnitude of this quantity, is the speed of light, which in atomic units that I've used is basically the inverse of the fine structure constant. So this one, you see that this term is 1 over c. This term is 1 over c cubed, so we expect it to be much smaller. This one is only 1 over c cubed squared, and this one I can show you it is also 1 over c squared. So actually, here there is some. I would like to make some comments. Here I put just ellipsis because you may ask, is this the right equation, or are we missing some terms? Because how do you know that there could be other effects in your system? Well, the answer is that if this is the right Hamiltonian, the answer is yes and no. In the sense that there is only one formulation which is fully correct, which is the Dirac Hamiltonian, so fully relativistic. And this is only an approximation of it. And the approximation in the sense that you are doing an expansion in 1 over c. So in principle, there is an infinite series of terms here, right? Going 1 over c to the 4th, to the cube, to the 5th, and so on. And then the answer is yes, it is the good Hamiltonian because we are expanding, sort of Taylor expansion. So sooner or later, this expansion will converge, right? So in some sense, we are still doing some approximation, but this is the right thing to do. Actually, there is a subtlety, because this kind of expansion would fail if you have a nucleus if the number of protons is 137, because why? Because you do a Taylor expansion on something which is not smaller, but we don't have nuclei that are so heavy, right? At least to my knowledge. But nevertheless, I think that if you go to uranium has a Z of 92, so 92 over 137, well, maybe one should retain more terms in this expansion. And actually, it is possible to show also that you can unify this Hamiltonian together with the NMR. And I don't explain all these terms. And if you are really interested, you have to look at the thesis of this Pekka Marinen, in which he did the derivation of all the possible terms up to order 6 in the speed of light. And there are 5 pages of tables like that. And yeah, well, I mean, if you have to do uranium, you have to do that. And basically, so let's have a look at some of these terms. Well, so this is just a partial listing. Just a partial listing of the terms which are ordered alpha squared. Alpha squared, remember, is 1 over c squared. So we just concentrate on these terms. And for instance, this term is the one that gives rise to the zero field splitting. So this is the coupling between two spins. And this is the hyperfine. I will show it later. So in the previous equation, we have also to add all these terms. And I'm pretty sure that if I remember correctly, in the next page of this table, there were the coupling with the nuclear spin. So you get still all the operators that Ari showed before. So the G-temp, I mean the chemical shift, the JJ coupling, and also the nuclear quadrupole. I mean, they all come out from the same theory, basically. It is very nice because it's a sort of unified way of seeing it. And okay, so let's try to understand how to calculate these parameters. So the easy part. From the effective spin Hamiltonian, if you remember, it's just alpha divided by 2 G S dot B. So basically, if you take right, in order to get G, I am simply to do the derivative with respect to B and with respect to S formally. Right? Here, so the G tensor is defined as the double derivative of the Hamiltonian, the energy, let's say, with respect to the spin and to the magnetic field. And here is the easy part, because the Zeeman term gives you just GE, so the G factor of the electron, multiplied by the unit tensor, so this is diagonal. The Zeeman kinetic is very easy, because it was just something multiplying B and S, and simply you get this one. And this TS is just the expectation value of the kinetic energy of your occupied manifold. And this S is the spin, is plus 1 half minus 1 half. This is the easy part. To implement these terms, it's really easy. Well, in order to get the S, the spin orbit and the spin other orbit contribution, we have to go back to linear response instead. Because the SO term, they do not depend explicitly on the magnetic field. They depend only through the wave functions. Because when you turn on a magnetic field, you perturb the wave functions. Now the wave function will depend on the magnetic field. And then you have to do perturbation theory. So this is basically the same slide that Ari showed. So this is the procedure. So you start from the ground state. Then you use the density function perturbation theory with respect to magnetic field in order to get the first order part of the wave function with respect to magnetic field. And from that you calculate the induced current, which now, for convenience, we separate into spin components. So we have the current carried by the spin up electrons and the current carried by the spin down electrons. And then, after 3 pages of algebra, you can prove that this is the final expression of the spin orbit contribution to the G tensor. So basically, you have a sum over the 2 spin channels, and you have to do this integral. So this is the current carried by spin S, and then you have to do this cross product with the electric field. And for the spin other term, you can prove that, this is also an approximation, you can prove that it's basically proportional to the induced magnetic field multiplied by the spin density. And if you are interested, you can write to me, I can send you some notes. This really takes 3 pages of algebra to do it correctly. And maybe to do it correctly with all the signs and all the i's in the right place, you have to do it 3 times maybe. So that's why. And so as Ari mentioned before, there is also, we also developed another method to calculate the G-tensor, which does not require to use linear response. Because basically what we had done before was to do this derivative this way. So basically first we have done the derivative of the energy with respect to spin, and then with respect to the magnetic field. So to do in the magnetic field we had to do the famous linear response. But we can circumvent the use of the linear response if you do it in the opposite. If you do it in the other way around. So first, if you do the derivative of the energy with respect to the magnetic field, you get minus the magnetization of your system. And then after that, you do the derivative of your magnetization with respect to the spin. Actually, this derivative you do it by finite differences. It's much easier than doing the linear response. And the total magnetization, I remind you, is the sum of the spin plus the orbital part. So the derivative of the spin part with respect to spin, not surprisingly, gives you GE, the G factor of the free electron. And what is left is the delta, is the spin orbit contribution. So as I said, so basically we approximated this derivative by finite differences. Basically, I constrain my spin to be up, and then I calculated the magnetization, and then I constrain my spin to be down, and then I calculate the orbital magnetization. I take the difference, the derivative, and this gives me the contribution. The way to calculate it, I will not enter into details, has been formulated only recently. Is the modern theory of the orbital magnetization. The price to pay is that you have to do a calculation including spin orbit in a ground state, which is actually a good thing to do, because in the previous formulation, the spin orbit was entering only to perturbation theory, so was only entering infinitesimally in your system. But if, for instance, if you go to very heavy elements like gold, silver, and so on, you already need the spin orbit in the ground state calculation because the bands are split already there. So the electronic structure, so in order to get to the ground state, you need already spin orbit. The second advantage is that here you don't apply any magnetic field, and so there is no gauge problem, which is very good, for instance, for the chemist people. And of course, you don't do linear response. I want to point out this because imagine you want to do some fancy calculation using some hybrid functionals. Well, I tell you that it's a nightmare to do linear response theory with hybrid functionals. I don't know even if it has been formulated up to now, probably. I know that the chemists, they do it with Hartree-Fock, and they get very complicated equations, right? So basically, in this way, you just need to do ground state calculations, so you can use the most complicated Hamiltonian you like it, and then you don't have to do linear response. And this is not implemented in the version that you are using, because it's still experimental. And if you are interested, basically you can ask me, I can send you the code and show you how to use it. The last parameter is the zero field splitting, which actually, if you think about it, is similar to the quadrupole in MR. So there is the coupling of two nuclear spins. Here is the coupling whenever you have more than two unpaired spins. This is the expression of the coupling. So this term is very difficult because it's like Hartree-Fock. So it depends on the relative distance between two electrons. So it's a 2 electron, requires to do 2 electron integrals. And people usually say that this term is small, so we don't compute it. But my impression is that when you don't know how to compute a term, you just state that it's probably very small. And it's not, believe me, sometimes. And this is not yet implemented. So this is very difficult and very, very time consuming. Can be simplified if you have just tripled states. This expression can be simplified, and there are ways to calculate it. But in the general case, it's a nightmare. So that you always said this is negligible, right? And so let's see, for instance, these two methods for the G-tensor, how do they work in two simple cases. So in this table, I'm showing the two radicals. So the Cn radical. So all these two molecules, they have an odd number of electrons. So they have unpaired electrons. But the difference is that in the case of the Cn molecule, this unpaired electron stays only one in a sigma orbital, which is 1/4 degenerate, right? L equals 0. In the case of the CF, carbon fluoride radical, this is very interesting because the ground state is a pi state, so it's 2-fold degenerate because it's perpendicular to the axis of the molecule. So you have one electron into two states. So in principle, one should use degenerate perturbation theory, which is not what is implemented in quantum espresso. And in fact, I mean, if you use the linear response technique, which is this column, basically this technique fails to get the G tensor of this molecule. This is because you have an energy denominator which goes to 0. Right? If you remember the Green function, any kind of perturbation theory, you have sum over empty states, and then you have energy denominator. But if you have a state which is half filled and half full, so the energy denominator goes to 0. So that in principle that goes to infinity. And instead, if you use the converse method, so the one I told you that I fix the spin in one direction, and then I just flip it, and then I calculate the optimization, well, we get the right value. In this molecule, it is interesting to look at the parallel component of the G tensor. It is 0, and you can prove it that it must be 0, because basically what's happening is that the angular momentum is pointing in this direction, and the spin is pointing exactly in the opposite direction. And why it is this important? This is not just because of the illustration, because there are many systems in which the G tensor has large deviation from 2. And this signals the fact that the ground state can be degenerated. So if you have a system with a very large, with G tensor very different from 2, you cannot use linear response, because linear response will give you something which is always close to 2. Because this is the way we expand it. Our reference state is a state in which the electron starts from GE, so the G tensor of the free electron, and then we just give you correction with respect to the value. Only if you go beyond perturbation theory you can get the right results in this case. So the last parameter that I will discuss today is the hyperfine coupling, and this is also very, very important in my opinion. And also here, formally, the hyperfine coupling is defined as the derivative of your energy with respect to electronic spin and one nuclear spin, right? And conventionally, this is decomposed in 2 terms. So one term which is diagonal, so this is the unit tensor, and the other term is called dipolar, which has no trace, 0 trace. And this is the expression that you can find on many books, and also on the thesis. So basically, the isotropic term is the Fermi contact term. It's given basically by the product of 2 magnetic moments. So this is the magnetic moment of the electron. This is the Bohr magneton. This is the G factor of the electron. This is the G factor of the nuclei, and these are all tabulated. These are all, in the era of nuclear physics, they were all measured and calculated also. And this is the nuclear magneton. So this is the product of 2 magnetic moments. You have to divide by the spin multiplicity. 4 pi over 3, not surprising, the comes of integration into a sphere. And basically what you have to take is the spin density, which is the difference between the up density and the down density, delta over r, at the position of the nuclei. This is called the Fermi contact term. And this is very important to study electronic structure, because remember that only the s orbitals, they have a finite density on the nuclei. P and d orbital, they have nodes on the nuclei, right? So basically, the Fermi contact term can tell you how much S wave function you have in your system. So it can give you basically the hybridization of your system. The second term is the dipolar term, comes from the expansion of a nuclear dipole, is given by this expression. Here again you have the spin density, and now you have to integrate this expression, but this R over 5 goes down very quickly in space, so basically this quantity is basically living inside a very narrow region close to the nuclei. So before going on, I remind you that all this you have to do it with either you do it with all electron methods, or if you want to do pseudopotential, you have to do the reconstruction. So like we do for NMR, because this for sure, because you need to know the density of the nucleus, and in pseudopotential you don't have it. It is just wrong, the density of the nucleus. So in all these nuclear spectroscopies, EPR and NMR, you need to do reconstruction and all electron orbitals, which I will not cover in my talk. But then I started to calculate some hyperfine couplings in some molecules, and then I didn't get a good agreement at the beginning. And then I was thinking, well, maybe that's the way it is. That's the functional theory. We have some problem. But then I soon realized that it was very well known in literature that there is an extra effect here. So that is, when you polarize one with valence electrons, In the pseudo-potential approximation, right, we freeze the core. We don't allow the core to change shape, right? So the core electrons, they have the same energy, same eigenvalue. There are no net magnetization in the core. But then if you just take the LD1 code that can be used not only to create pseudo-potential but also to do atomic calculations, you convince yourself that this is not the truth. For instance, take the lithium atom. So the lithium atom has 1 electron in the 2s orbital and 0 electron in the down channel. Well, the hyperfine coupling basically becomes everything from the 2s. This is reasonable, right? Because the 2s is the only one that can give you some hyperfine coupling. So, and this is the total one. But take, for instance, carbon. Now you are putting 2 up electrons in the p orbital. The p orbital, in principle, has a node at the nucleus, so it should give you 0 hyperfine. But it creates an internal exchange field, an internal magnetic field inside the atom. And this magnetic field splits a little bit the 2s orbital. And this we can capture using reconstruction and people. But surprisingly, the 1s orbital, acts in the opposite way, almost to cancel the hyperfine coupling of the 2s orbital. Now you see the problem, because you don't want to create a pseudo potential which you put also the 1s in the core, right? It will be extremely hard. But then it looks like that this core relaxation is not, is not negligible, it's not small, and then it also varies across. So the case of sodium is like this, the case of lithium, right? We are just going down one row in the periodic table, so almost everything comes from the 3s. And again, silicon is similar to carbon, so the 3s is split, but then there is a non-negligible contribution from the 2s and the 1s. Right? In the pseudo-potential of silicon, you don't put the 2s in the valence, right? And here is magnesium, for instance, because I'm very much interested in doing magnesium clusters. And in magnesium, okay, you do semi-core. In principle, these are valence electrons, but in order to get a good electronic structure, you put also the 3s. These are called semi-core pseudo-potentials. But you don't want absolutely to put the 2s in the pseudo-potential. And then I was hoping this number to be almost the same, ranging across all the oxidation number and configuration, but well, actually it's not the same, so this is a problem. And this is the illustration why. So this is remember, we are polarizing the 3D orbital. We are putting, for instance, 5 electrons into the 3D orbital. The 3 orbital has a large overlap with the 3s, so that's why we have to include the semi-core. And then, it has some influence on the 4s. But now, but then look at the 2, this is the 2s orbital, which is basically, you could say, the 3D orbital is leaving this region of space, the 2s orbital is there, they don't talk each other. But then, if you actually compute the difference of the potential seen by the 2s electron, which is given like this, basically, this is the exchange correlation potential up minus down. So this has a large contribution also in the region of the 2s. So this is why, this is how the magnetization of the 3D is able to affect also the very low-lying core orbitals. And basically, so one has to go further on with respect to the Gibov approximation. So one has to do not only the reconstruction, but also try to relax the core. And this is the way we've done. Basically, we computed the spin density, reconstructed, and then we basically compute on a logarithmic grid, on a radial grid, the perturbation, so this delta V. And with this delta V, we do perturbation theory on the core orbitals only. Also, this one is not yet, I didn't include it yet in Espresso 4.1 because it's still experimental, because I have some troubles to understand why this method works, because this is perturbation theory, so U runs on the core orbitals, and V runs on the other orbitals that are different for you, but in principle you should sum up to infinity. So I call it incomplete perturbation theory, and then I don't understand why I get good values out of it, because in principle one should sum also over the unbound states. And I have no evidence that this matrix element goes to 0 as you go up in energy. I have no evidence, I have no proof, but this is the way it works, for instance. So here is the Fermi content, for instance, from some small radicals. Actually, I should not show this one, the CH2 molecule. And you can appreciate here the effect when you do the core relaxation. So, for instance, this CH radical goes from 200 to 90. Okay, it's not perfect, but it's not bad. Okay, in the case of hydrogen, there is no core, so the two numbers are the same. But for instance, look at here. Here, I mean, the improvement is fantastic. Okay, here is okay, it's already very good. Yeah, in this case, I mean, there is not much difference between the. Another way of representing it is these typical plots in which you put here the experimental hyperfine coupling and the calculated one. So the red points are without the co-relaxation. And there, I mean, they follow the diagonal, but they are a little bit scattered. But of course, I mean, if you look at it, I mean, the blue points, which I included the correction, are much better. So unfortunately, I'm not yet put this in expression because I'm not sure if it works for every system. So one must be very careful. So if you want to use it, please ask me. And this is the dipolar terms. So apparently in the dipolar terms, you don't need to do any co-relaxation. They are already very good. I mean, good agreement with experiments. These are probably a few percent from experiments. And right. So why EPR is so important, in my opinion? I want to share with you some my personal thoughts with that. There is in the past years there have been a lot of functionals in development in functionals, right? We have hybrid functionals and so on. They're all fitted to produce the thermochemistry of your molecule, that is to produce total energies, structures, energy barriers, and so on, which is very good. But what about the electronic structure that you get? I mean, the total energy is not just the end of the story, in my opinion. And this is one attempt to go beyond DFT. So since I can use any complicated Hamiltonian I like in my calculation, so I try to do some ADA plus U that have been explained to you the week before, and to do it on these manganese oxide molecules. So I don't enter into the details of these numbers. So these are difficult systems for DFT because there is a lot of self-interaction, self-exchange, also correlation. And believe me, these systems are difficult also for couple cluster methods. Couple cluster, no one tells you, but they are not meant to be done for open shells. This is never written in any paper. So couple cluster works very well for closed shell systems. And this is what we observed. So in this plot, I'm for instance showing you the absolute magnetization of my molecules as a function of the upper field. And these molecules, they basically clusterize into two classes. So these are high spin compounds, which you have very high 3, 4, or 5 ampere spins, and they're all aligned. And there are a couple of molecules. This one, which is the MnO3 molecule, is sort of borderline. It doesn't really know if he wants to. It doesn't really know if to be a low spin or high spin. But then there are a couple of molecules here which are so-called low spin compounds, which they are basically antiferromantic. They have only, for instance, spin 1/2. And here there is a nice failure of ADA plus U, which is this yellow line here. This MnO3 minus molecule is a closed shell. It has no ampere spins. But then, as you turn on the Albert U, you get some ionization, which is wrong. And now we are trying to understand why it is so. But basically, this comes from the fact that ADA plus U and also local spin density is basically an unrestricted method. And unrestricted wave functions are not eigenstate of SZ, of S squared. So basically, what the unrestricted wave function does, it also mixes other multiplicities. And this is wrong. But it's not completely wrong because the reality is this one. Because spin densities, they do exist, and they have opposite signs. This means that the real wave function, the real many-body wave function, it has a little bit of spin contamination. And basically, this quantity I'm plotting in the vertical axis is the so-called absolute magnetization. If you remember, when you run PWSCF, it gives you two numbers, right? The total magnetization and the absolute magnetization. For the total magnetization, it is clear, right? It's how much magnetization you have. The absolute one is when you take the absolute value inside the integral. And this is a cartoon to explain it. So if you have a covalent bond, right, the up and down wave function, they have the same spatial shape, right? So that this is 0, but also this is 0, right? Because they have the same orbital, they have the same shape. If I have a radical, for instance, this is the OH radical, I have 1 ampere electron. So what I have that the total magnetization is 1 because it comes from this ampere electron. And then this ampere electron lives on a wave function on its own. There is no down electron. And so the absolute magnetization, also this one is close to 1. But consider, for instance, this system which is antiferromagnetic. In this case, there is no total magnetization because the two spins are opposite. But if I compute this quantity, since I take the absolute value on every side, I get something which is largely different from zero. So the chemists, they name this quantity spin contamination, and instead in the language of the physicists, this is called the antiferromagnetic order parameter, basically, right? Because you do this absolute value. And now here is clearly failure. So this molecule has no ampere spins, but at a certain point it gets some net magnetization, localized moments. And okay, let's see. I mean, how does the EPR performs on this molecule? So these are the good one. And this table is a little bit busy, but let's concentrate. I mean, on the most important parameter is this one, the isotopic hyperfine coupling. This is the MNH and MNO. So these are high spin molecules. They work very well. And in fact, I mean, if I calculate the self-consistent upper U and then I plug it in, I get a very good agreement with experiments, right? This is really off, and then I mean, it gets very close. So look, for instance, here. So at U equals 0, this molecule has 5 ampere spins, and then the absolute magnetization is 5.2. Good enough. Then I turn on the upper U, I get 6. So it starts mixing some configuration. That is probably the right way to do it. So the good, the ugly. guess will be the next one. Okay. So the MnO2 molecule. So here, experimentally, there are known several isomers. So the ground state is this one. The molecule is bent, and these are all excited states. So they are very close in energy. So in this case, I wanted to see is the hyperfine, the EPR spectroscopy accurate? Sensitive enough to distinguish between all these molecules? The answer is yes, because if I look at the hyperfine couplings, this is on the order of 800. This is 1000. This is minus 1000. So maybe this one can be sort of confused with this one, but this one has a different number of ampere spins. So let's rule out this one. So unfortunately, experimentally, there is only this value which is known. And experimentally, they don't know if it belongs to this one or to this one. And it looks like that the right answer is this one, right? So that is the bent molecule when I turn on the upper U. So unfortunately, this is not the ground state with 88 plus U. The ground state with 88 plus U is this one. So this is a case in which your function not only is wrong in the thermochemistry, but it's also wrong in the, it gives you the right wave function, but the wrong thermochemistry. And this is something that one should really care about. This is not that one. But look at this one. This has 1 ampere spin. If I have U equals 0, there is very little spin contamination. And then I turn on the upper U, and then I get 4 as an absolute magnetization. This is clearly too much. And in fact, we find out that of course, there is sort of overcorrection. So this goes down, but it goes too down. They are sort of overcorrection. We find out that you can have problem also if you do coupled clusters. So basically, depending on the parameters of your Gaussian calculation, if you can restart it and you can play a little bit with convergence, you can basically jump onto different solutions. And the right one is this one. Instead, this one that I obtained with 80 plus U looks like this one. So this one, also in Gaussian calculation, is very much spin contaminated. So I think this is not the right ground state. So this sort of showed up that if you want really to be, the spectroscopies, they are not there just to compare to experiments. So theory should compare not only to experiments but also calculation should compare to experiments but also to theory, in my opinion. But this shows you that you can have a very nice function that gives you a lot of good properties, but it gets wrong all the spectroscopic properties. So I think that we need to test functions also on spectroscopic properties that are optical, magnetic, vibrational, not only on the total energies. And as I said before, this is because the starting point is unrestricted. So one possibility is to do some restricted open shell, sort of try to reduce this sort of unbalance between up and down. But this would not work because a restricted theory will give you only positive spin density because the spin will be only in one channel, so the down channel will be 0. So my idea was to add a constraint like that. So I tried to push s plus 1, so I tried to push s squared towards the right value. I realized that this is nothing else than adding the j to the LDA plus u, so taking some. And of course, I could do hybrid function, but I'm not going to do it because they are too expensive. I mean, and then you never know what was the outcome of this hybrid function. But in principle, one can do it.
To look at the effect of spin contamination,
yeah.
You mean that this method would be suitable also to look at the Magnon dispersion?
Yeah, for sure.
Have you done any Magnon dispersion?
Well, at least for simple methods like iron, they have been done with the LDA in the past. They are really good.
And other point is, so far, like in superconducting nanoparticles, whatever, in superconducting system, experimentally, as I know, people are not able to see the charge density wave and spin density wave decoupled. People are not able to decouple them. Is it a kind of, it can go beyond that level so that you will see that when the spins are getting contaminated, really charge density and spin density.
So, in some sense, we also said yesterday that density function is not made for superconductors, but one can do some LDA plus something, right? Which is now becoming very popular. For instance, LDA plus dynamic field theory, LDA plus Gutzwiller. So these, if you go beyond DFT, you may have some chance to compute this quantity and then to compare to experiments. But what they do experiments, I mean, they are able to do NMR or EPR on superconductors. The problem is that in the field of superconductors, they do a lot of NMR, they do a lot of nuclear quadruple resonance, but just to find the magnetic phase transitions. They don't care about the chemical shift. They just measure basically the overall susceptibility, magnetization. They cool down and they find all the Nel transition, antiferromagnetic transition, ferromagnetic transition, spin order, spin stripe transition. This is the only use of NMR in the field of superconductors, unfortunately. So the experiment, they don't look at the chemical shifts. They just look at the
there are a couple of reports where they look at really the D wave and
there are very, very few, right? Very few experiments.
But they are the very good experiment in recent times. So
yeah, but the point is that also the electronic structure, probably one has to go beyond ADA plus dynamic and field theory, and to include the effect of correlations. So the part 2, I think I will take just 10 minutes and then we are over. So actually, this has already been discussed by Ari, so I apologize for having the same slides here. Okay, and then we get to the input of an EPR calculation. And the input is not difficult, as I said before. This is, for instance, the immunoradical, which is shown here. These are 1 ampere electron. So GIP of code is a sort of, it's like the phonon code. So first you have to do a ground state calculation. So first you have to run the WSCF. So this is a radical with an ampere spin. So you have to say that, okay, next number of spin equal 2. And then, I mean, I just counted the number at 11, and so that I have 6 up and 5 down. Or you can specify multiplicity equal to. So these are, you know that either you specify the number of up and down electrons, or you specify multiplicity in the input. And then, okay, also in the ground state, you have to start using immediately impulse field potential, which are not conserving. By the way, generally, the cutoff needed to do this calculation is slightly higher than the cutoff needed to get the structure. You have to go, if you have oxygen, you have to go to 90, 100. But you do it only for the EPR. You don't need it for the relaxation, for instance. And then, if one wants to calculate the EPR, this looks like very similar. It is very similar to the NMR input file. You just change here the job, I mean, the kind of calculation, to EPR. We have, I mean, this is the prefix for the name of the output files, the directories. Again, here it's done by linear response, so there is this small q that, but the default value is 0.01. It's already good. And this will calculate the EPR from you. I mean, we stay there for 1 hour and without saying anything. And just in the end, we just spit out a lot of numbers. For the hyperfine, you have to put a few more parameters. Okay, the job is now is called hyperfan, so they switch on the calculation of hyperfan. So here I forgot, I left the QGIF, but the hyperfan are not linear response. They are much faster. They are not linear response. So in principle, you do need each parameter here. So you can choose the unit of the output, because experimental is just to simplify our life for the user. They measure energy in frequencies, in magnetic fields, in apples, and something to simplify our lives. And here, for each atomic space, so the first one is carbon, the second one is nitrogen, and the third one is hydrogen. You have to enter the nuclear G factors that you can find on web elements. So they tell you what is the ratio between, let's say, the magnetic moment of the nucleus and its angular momentum. And these are all tabulated, thanks to the nuclear physicists of the past and the 50s. They are all there. And then, so that you can run, okay, the ground state calculation, then you run the GitHub calculation to do the EPR, and then you can also run on the other one, or the other way around. It's up to you. So, this is an extract from the output. So, this term here is diagonal. This is the Zeeman kinetic energy term. Remember that diagonal, so it's not a tensor, it's just a number. And we also implement a heap of reconstruction methodology, which gives you, a very small correction. And then we start with the various contributions. So also, like in the case of NMR, so we have pair, magnetic and parametric correction. But what really matters is the sum of them, because this is just, a conventional separation. So these are the contribution to the delta G. And then there is the spin anaerobic term. And then in the end, the code prints the sum of all this one. And so as in a form of a tensor, right? And these are in part per million. So these are the deviations from this value in part per million. So you have to divide by 10 to the 6. And by this, then you can compare to experiments. For the hyperfine, okay, the code simply reports, the atom which you're calculating the hyperfine. It reports you the nuclear G tensor that you have entered the input, just in case made a mistake, because you can rescale everything by if you don't mistake. And these are the unit of measure. And then it shows a tensor, which is the dipolar part. If you look at the trace of this tensor is 0. Minus 18 plus 2 plus 16. And then these are the eigenvalue. I think these are the eigenvalue of this tensor, but in this case this diagonal. And then it gives you the Fermi contact term. So the bare term is basically always very small, very negligible. There is the reconstruction part and the total, which is basically that one. So that shows that in this molecule, so carbon has minus 73 megahertz. The same for nitrogen, the same for hydrogen. Notice that hydrogen is very large. This is because hydrogen has one s electron, right? So the s electrons are the only one that really contribute to the hyperfine. And then you can also have a pictorial interpretation of this one if you plot, for instance, the spin density. And this will be one of exercise this afternoon. So this spin density, so red, I think blue is positive, red is negative, but we don't care. So if you look at the ampere spins, mostly lives on the lone pair of hydrogen. So this is a p orbital, which is parallel to the plane of the molecule. And it lives on a pz orbital on carbon, much less, and the sign is opposite. And the ampere electron spends most of this time, you see, actually on the s orbitals of hydrogen. So this is why. So this has the shape of a s orbital, so it has a large Fermi contact. Those one are p-type orbitals. They have a smaller Fermi contact, and this shows you that basically you can basically work out what is the hybridization of your system. How much S, how much SP you have. And this is very powerful technique because it is a spectroscopy that can really access the wave function. And I think I'm done. Yes. So if you want to know more, I put here in this section with the bibliography some books. Most of them you can also find, if you don't find them in your library, you can find them on peer-to-peer websites in deja vu format. Or you should not that. This is, if you are interested to understand, where the Hamiltonian comes out, I really suggest you to read this thesis. I just want to point out that I mean, if you are a physicist, you mostly do this. This is the transformation you do. So you start from the Dirac equation, you do this transformation, you get the Pauli equation. This is the physicist way. The Pauli equation is not variational. So in principle, it's questionable to use spin orbit in this way. And I was told that by some chemists that there is a much, say, a variational method which is called the Douglas cross code Hess method. This is implemented in some codes, and this is strictly variational. So basically, it's another kind of transformation of the Dirac equation. It gets you the terms. They look slightly different. So the expression of the several terms. But what is important is that numerically they will all give you very similar results. But in principle, this is variational. Okay, the theory of EPR parameters was firstly formulated the way I show you today. It was in this paper, and then it was done the same way in this paper by Francesco Maue. And this is to discuss the spinale orbit. These references have been shown also by Ari. And finally, I mean, if you are interested in this, there is the converse approach and the model theory of the organization. All right, I'm done. So, questions? Questions?
Can you calculate this with quantum Monte Carlo? The EPR? With the orbital magnetization?
Right, yeah. But you need the complex wave functions.
Okay.
If you have a code with complex wave function, you can do it.
Have you done?
No, because I mean, well, this is an idea of Nicola, but so Carlia Filippi was very interested in it. But they have only, I mean, a quantum Monte Carlo code with real wave functions. So yeah, that's the point, because then you just have the same problem, but then with complex wave function you have the phase problem, and it's more difficult. But this could be possible. Yeah.